Hello everyone. We're going to start our next topic, which is topic 3 on logic and probability, and we're going to start by talking about sections 8.1 and 8.2. Now, a lot of chapter 8 is on probability, but before we can start talking about probability, we first need to talk about a couple things. So the first thing we need to talk about is what a set is. So a set is just a collection of objects, and those objects can be anything. It can be numbers, letters, names, etc. It can be anything. Those objects within a set are called the elements of a set. Okay, so that's what the objects are called. Now, in order to see how many things are in a set, we use this notation right here, NA. And what that means is just the number of elements in a set. Okay, so as you can see, we have a capital letter for A. That is how we use letters to name sets. So we use capital letters for sets, and we use lowercase for elements or objects within that set. So let's look at a couple examples of sets. Right, so here's the first example. Positive integers, that's what this plus here means, only the positive integers, so like 1, 2, 3, 4, and so on. Now this set, because it continues forever, has an infinite number of sets, and this should be the positive integer set. It has an infinite number, so since it has an infinite number of elements within the set, we call it, we call it an infinite set, since the number of elements is infinite. Now our next example here is just this set A. Set A equals 1, 2, 3, 4, 5. And this has exactly 5 elements in it. So we call this a finite set, since it has exactly a finite number of elements. Here's another example. C. We could have just the names of absent students in a class period. Another example we have is set D here. Now the way that set D is written, this is called set builder notation. And this is one way to list all of the elements within a set. So one way that we saw, we could just make a list of all of the elements in a set. We can also write a description of the elements within that set. So just like this, in example C, so names of absent students is a description. And the last way we can do this is with set builder notation. Okay, now this line right here in set builder notation, that stands for the term such that. So what this says, it says X such that X is between 0 and 5, including 0 and 5, including because of this equal to line. All right, so 3 ways we can name elements in a set. We have an infinite set here with an infinite number of elements within it. We have a finite set with a finite number of sets in it. And then also make note that we have something called set builder notation as well. Okay. So there's something called the empty set. The empty set is a set with the number of elements equal to 0. So there are no elements within that set. So an example of an empty set is a set F, which is all of the prime numbers that are multiples of 10. All right. So because there are actually no prime numbers that are multiples of 10, because then we would have more than one factor of that number besides 1 and itself. The number in set F equals 0. So what that means, that determines that F is the empty set. And we use this symbol right here, kind of looks like a 0 with a line through it, to denote the empty set. Okay. So we're going to do an example of writing a set in set builder notation right here. So we're going to do that in class. So I'd like you to write it down, and then we'll do it in class next time I see you. Okay. Now let's talk about specific types of sets that there are. There's something called the universal set here. Now the universal set, we use U, a U for universal, to denote it. This contains all possible elements for a given problem, so just that given situation. All right, so an example. So say our universal set is all of the numbers x such that x is less than 10 and x is a natural number. So remember, natural numbers are counting numbers from 0 onwards. So that would mean the elements in set U in our universal set for this particular problem. Now remember, it's just for this problem. Are the numbers 0, because we're talking natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Not 10, because this is strictly less than, rather than less than or equal to. And we're talking about just whole numbers because we're talking about natural numbers. So for this situation, if we were to do some more problem here, or some problem with this, this would be the universal set, which means that the problem we're doing only focuses on these numbers and nothing else. Right? We could have a subset of numbers or of a situation. So a subset is a set where every element within that set is also an element of another. And there's a symbol for a subset, and that symbol kind of looks like a sideways U with a line underneath it. Sideways U. So think of this line as meaning equal. Okay, so there's two types of subset. There's just a subset, which could also equal the larger set. And then there's something called a proper subset, which is a subset that is not identical to the original. So I could have an example if we were looking at this example up here that we just did, our universal set. I could say A is a subset of U as long as A has numbers within U. So if it's a proper subset, which uses just the sideways U, not the equal sign below it, that means that there are elements in A that are not, or elements in A, but there are even more elements in U. So for example, if A was odd numbers, so 1, 3, 5, 7, 9, A is a proper subset because there are more elements in U that are not in set A. So it is a proper subset. So remember, the term sub means like within and below. So some important notes. So if something is a subset of another one, then two things happen. One, every element lies in the bigger one. So every element in this example here lies in our universal set. So every element in the smaller set lies in the larger. And there are some elements in the larger one that do not lie in the smaller, which is true for this example up here as well. Right? So a very useful tool to help us identify sets and elements within sets are Venn diagrams. So this is a Venn diagram. In this Venn diagram, there should be another circle right here for M. In this Venn diagram, M, N, and A are all subsets. So they are within the universal set U. So in Venn diagrams, we use a rectangle, this entire rectangle, to represent the universal set, so every element within a situation. And we use circles within that to represent subsets. So I could say in this situation, since M is inside set N, M is a subset of N, which is also a subset of set U, the universal set. An important note to take, something important to note, let me just move this up a little bit for you. The empty set, not zero, the empty set, remember that's the symbol for the empty set, looks like a zero with a line through it, is a subset of every single set, and every set is a subset of itself. This is just something to take note of. So we can use these Venn diagrams to look at specific sets. So for example, the complement of set M. Okay, so the complement of set M is every element not in set M. So if I use my highlighter here, this circle represents every element within set M. So the complement would be every single element outside of that. So everything outside of that circle, I'm going to highlight, and that is the complement. So everything not in the set. And we use an apostrophe right here to denote the complement. Okay. The intersection of two sets, which looks like an upside down U, are all of the elements that both sets, or all of the sets you're talking about, have in common. So let's look at our example right here. Okay, there we go. So I'm going to highlight set M in blue. So everything in set M in blue. And I'm going to highlight everything in set N in green. Okay, so everything in set N is in green here. Now where the two overlap, they overlap right here in the middle in pink. The overlapping portion is the intersection. This is how you denote the intersection. Okay, where the two overlap. So think, when you hear intersection, think overlap. So the elements that are in both M and N. So and is that key word there. The union are all the elements in either sets M or N or both. Okay, so think the word or. So here's our example here. So I'm going to highlight, again, using the same colors. I'm going to highlight everything in set M in blue, everything in set N in green. The union was kind of nice. Think of the union as all of the elements that you just highlighted. So the union is everything in set M or set N or in both of them. So it's everything that we just highlighted right there. So everything in both of those sets. All right. So again, think all together. So all of the elements all together in all of those sets that you're talking about. And the key word there is or. Okay. Now I did forget to write one thing down here. We can see everything right now in the complement, everything not in set M. And if I included everything in set M, that would include everything in the universal set. So we like to say that set M plus its complement, that apostrophe, equals the union. Or I'm sorry, the universal set. All right. So again, intersection, think and, with the upside down U. Union, think or. And this is how you write it. It looks like a U. So intersection and, union or. And that's everything on sets and how we can represent them using Venn diagrams. So we're going to do an example in class, but I would like you to write it down. So here's our example we're going to do in class. So our universal set is X such that x is less than 9 and a positive integer, so all of those numbers. A is the set of even numbers, B is the factors of 18, and A and B are both subsets of U. So that means that these even numbers and these factors of 18 are also within this situation here. So are also numbers less than 9 and positive integers. So what we're going to do with those values is we're going to first list the elements in each set. Then we're going to represent them on a Venn diagram and put those actual numbers where they should go in the Venn diagram. And then we're going to shade the regions and list the elements of each of these situations. So the union of B, the intersection of both complements, and the union of the complement of A